Good day, folks. Welcome to Parades Mind Academy, where we bring brilliance to every lesson. Now, in today's video, we're going to be doing question papers under a topic that we call now reaction rate, okay, or rate of reaction or reaction rate. Now, without wasting any further time, this is supposed to be a short video, like something like 15 minutes or so, okay, but it can be long because I like to explain. Learners use the reaction of a sodium thiosulfate, or however it is called, solution with dilute hydrochloric acid to investigate several factors that affect the rate of reaction, of a chemical reaction rather. The balanced equation it is given as that, right? Okay, cool. 1.1.1 says define reaction rate. This is true or nothing. It's either you get it correct or you get zero. So how do you define this? This is let me do this. The change in concentration of products or reactants per what? Reactants per what? Per unit time. Very important. The change in concentration of products or reactants per unit time. Can you see now? You miss per unit time, you get zero. I'm telling you, I'm not asking you. Know your definition of by heart. The investigations 1, 2, 3 are carried out. Okay, now 1.11.2, let's look at investigation 1. So the results obtained in investigation 1 are shown in the graph, okay? Graph of the reaction rate versus the concentration of sodium thiosulfate, if I remember very well. Yes, thiosulfate solution, the off, okay? So now remember I said the reaction rate and the concentration or whatever the effect will increase. Why? Because check, as you increase the amount of concentration here, okay, as you increase your concentration, remember you are increasing the effective collisions, okay, and if there are more effective collisions per unit time, there is what? There is a higher reaction rate. So for this investigation, write down the dependent variable. Always, not sometimes, always in this topic of reaction rate, the dependent variable will be what? Will be your reaction rate or rate of reaction. Your reaction rate will always be your dependent variable. Even if you can check, the y is your dependent, the x is your independent. Why? When we change the concentration, the reaction rate changes. We cannot change the we do not say as the reaction rate increases, the concentration increases. How can you change the reaction rate of reaction? Because you need something to affect it, whether positively or negatively. Okay. Now 1.2.2 says write down the conclusion that can be drawn from the graph. You can see that uh, an increase in concentration of what? Okay, let me write in word. An increase in concentration of sodium thiosulfate. An increase in concentration of sodium thiosulfate increases the what? The reaction rate. Very good and easy to max. Okay. 11.3. Maxwell-Boltzmann curve. Maxwell-Boltzmann distribution curve. Now for investigation 2, we have the Maxwell-Boltzmann distribution curve A and B. A and B represents the number of particles against kinetic energy for the reaction. Okay, we know this is number of particles, this is kinetic energy. Now remember these. Remember, if we do not look at the question, we know this area means now particles that undergo effective what? Collision. That have what? It means they have what? kinetic energy that is greater or equal to the what? Activation energy. They told you even also here. This P means what? This is our activation energy. We know this is our activation energy there. Then now I know this graph I can only attain it if the effect is temperature. Why? Because the concentration is like this. It's like this. The other one may be like this or like that. For temperature, it's either it is the first one is like this. Okay, the first one is like this. If the temperature is increased, it becomes shorter and narrower like that. Then if the temperature is decreased, it becomes like that. Okay, I know. So this one is the temperature. So this one, if I were to compare these two, this one is, can you see it has the highest peak and it is narrower. So can you see also it has fewer effective collisions. So it means this one, it is what? This one, it is cold. This one, B, it is hot. Okay. Yes. Okay, I'm done. What does line P represent? Remember, line P always represent what? Activation. You can write it in full: activation energy. Which curve, A or B, was obtained at a higher temperature? Curve B. Curve B. Why curve B? Why curve B? Because now, can you see there are more effective collisions that occurs per unit time? Can you see for graph B? The particles that have a sufficient kinetic energy, that is, that undergoes a effective collision. Can you see how many are they? There are many of them. Okay, yes. So now they say to us, explain in terms of collision theory. Why are we saying that? Okay, okay. Explain in terms of collision theory how, and they already give you, they already gave you the effect. How an increase in temperature influences the rate of reaction. Okay, what happens at an increased temperature? Remember, always when they say increased temperature, you make an example of cold water and hot water. If you're not so sure about this, please look at my video where I recorded explaining the concept. Remember, cold water moves slow, but hot water moves faster. Okay, so we say the what? The average kinetic energy. Kinetic energy of particles increases, or particles moves faster. But I want to include kinetic energy because I know I'm gonna use it somewhere. Therefore, if the average kinetic energy of particles increases, it means now there will be more particles with sufficient kinetic energy that is greater or equal to the activation energy. Okay, instead of writing all those words, I'll say more particles with what? Kinetic energy that is greater or equal to the activation energy. Remember, activation energy, you can do this or you can say EA, it's fine. Okay, now if there are more particles with sufficient kinetic energy than the activation energy, remember this is one of the conditions needed for effective collision. So there will be more effective. Remember, there is a question that you should ask yourself: more effective collisions per what? Okay, per unit time. Remember, I said when you arrive at number 3, always note sometimes number three and number 4, they do not change. They're always like this. What changes is whether it is less effective collision and a higher reaction rate or low. Okay. Therefore, if more effective collisions occur per unit what? Time, therefore higher reaction rate. Reaction rate, or you can say the reaction rate increases. I want to believe you are following. This is supposed to be nice and easy and fast. Then the last investigation number 3, the potential energy diagram X and Y represents the reaction under two different conditions. Okay, I can see the X, it is the original. Then the Y, it is under the influence of what? This one, there is a catalyst here. Remember, I know if I'm having a graph like this, what will a catalyst do? My catalyst will come and say, I'm going to shorten this up. Okay, so this one is under catalyst. Catalyst was added. In case they ask us, give a reason why graph Y differ from graph X. Indeed, indeed, indeed. There was the addition of a catalyst. Okay, there was. You do not say graph Y has a catalyst. There was an addition of catalyst on for graph Y. Okay. Now they say in one of the investigation, 100 centimeter cubed of 0.2 mole per decimeter cubed hydrochloric acid reacts with excess sodium thiosulfate in aqueous, and the solution is then filtered. Okay, so now they were doing that reaction. Okay, here is that reaction. So those two they reacted and formed products. Now, after forming those products, they filtered out the solution. It means they were trying to obtain something. Okay, let's hear. After filtration of the solution, 0.1 grams of sulfur is obtained. Okay, so as they were filtering the reactants that they got there, they got that the sulfur here. Okay, I forgot to include the phases. Okay, but sulfite is in solid. Sulfur and yeah, sulfite is in solid since we are using sulfur. This is solid, okay? So this is aqueous, this is aqueous. Okay, sulfite is in solid. So it means now as they were filtering there, sulfur particles uh, were the ones that were filtered, okay? Yes. So it means they obtained this much, okay? So this is what we call the one that they obtained. It is what we call the actual actual uh, yield. Okay, why are we saying yield? It is the actual yield that you get as you do the experiment. Okay, there is this one that we call a theoretical, us saying, okay, after if we do calculations, we expect that it is theoretical. We are doing it theoretically. Again, theoretically, we are just writing everything down. We are calculating. We are saying, okay, theoretically, we can obtain um 0.5 grams of sulfur if we do this experiment. But in real fact, the results do not necessarily come out like that. There is never 100% a percentage yield of what you calculate. What you calculate can never be exactly precise as what you get. Okay, can never, because why? There are some factors that affect the what our results there. Okay, yes. So they say calculate the percentage yield of sulfur. You have to remember the percentage yield before you move so that you know where to go. You already know the actual yield. So for percentage yield, the formula is actual yield, the one that we actually yield in the field, in the mining field, divided by the theoretical, the one that we believe or we think might be the outcome. We are estimating, sorry, multiply by 100 because this is the percentage. So now can you see now we only have the what? The actual yield, the one that they got throughout the process. Okay. So now it is just a matter of us to calculate the theoretical one. Okay. Okay. If we were to calculate theoretically how much would we expect to get. Okay. And this English this English makes me a starter man, and I'm not. Okay, I'm not saying status it is bad, but the way it is doing me so bad. But yeah, okay, never mind the starter thing, we are not there. Now what we can do is remember this is a limiting reagent. Oh, sorry, in this case HCl is the limiting. So it means we have to use information about this one because we have more information about this one. And what are we told about? Remember, in chemistry, every time all we want to get first in every information that you have, just convert whatever that you have, the information that you have, to number of moles. So just convert to number of moles. So for HCl, we have what? The volume in centimeter cubed and the concentration. So we can get what? Number of moles. So we can get, remember formula, it is C, it is equal to N divided by V, okay? So if I want the number of moles, I'm going to say number of moles of what? HCl. I like you to indicate what exactly you want number of moles of, okay? Number of moles is equal to CV, okay? When I just multiply this on the other side. So now, remember this, the volume should be in meters, okay? Decimeter, okay? Cubed. This one should be in mole per decimeter cubed. Now, when we check there, we have our concentration of S 0.02 mole per decimeter cubed. That is very good, and that's what we want. Okay, we have our concentration as 0.02 mole per decimeter cubed. Now, what is our volume? It is it is given as 100 centimeter cubed. This is, let me specify, this is volume of HCl. Okay, now what do you do from centimeter cubed to decimeter cubed? You just divide by what? By 1000. Okay, then you'll get that our volume in actual measurements that we require, it is 0.1 decimeter cubed. So you just say 0.1. Okay, then you get the number of moles of hydrochloric acid as how much? Is it 0.02 or 0.2? 0.2, sorry. So concentration here, it is 0.2. Ne? So the outcome is the one that is 0.02. I already saw the answer before. So we get what? Mole. Why? Because concentration, it is, when you multiply concentration by volume, concentration, it is mole per decimeter cubed. When you use dot, we take this one to the top. Multiply by volume, it is decimeter cubed. This and this cancel, so we get what? Moles. Okay, yes. This is our conversion, not important. Okay. Then, when I get the number of moles of hydrochloric acid, remember what am I trying to get? I'm trying to get the actual, sorry, not the actual, we already have. I'm trying to get the theoretical yield of what? Of S, of sulfur. Let me not call it like that, of sulfur in solid form, okay, of sulfur. But now, how can I do that? I have to use mole ratio. I have these and I want these. So I have to use mole ratio between mole ratio between what? HCl as well as what? As sulfur there. Okay? So now, what is the relationship? So I'm gonna say between HCl and the sulfur that I want, the ratio is 2:1, and I already know the number of moles of, remember the ratio, use it on number of moles. Okay, number of moles of HCl we just found as 0.02. The reason I like you to indicate here, it is the number of moles of what, it makes me, or the marker, easier to understand what they are marking. Okay, and it makes you to understand, to follow. If you want the number of moles of HCl, you just know, you check number of moles of HCl, good. Instead of calculating bunch of calculations and now trying to figure out which one is the number of moles of that one. Okay, yes. So this is 0.02, then this is what we are looking for. Okay, let's just put it x. So when you do your maths, it's gonna be 2 multiplied by x, it is 2x. Maths is not important, which is 0.02. Then x, it is equal to 0.01. So x, which is the number of moles of what? Of sulfur, it is equal to how much? 0.01 what moles, right? Now that I got the number of moles of sulfur, let me try to get the theoretical mass, okay? The theoretical mass of sulfur, because now they got actual mass, okay? If they got actual number of moles here, I was gonna try to find actual number of moles, okay? Theoretical rather. So here I'm gonna say, okay, let me try to find number of moles called mass over molar mass. What am I trying to calculate for here? I'm trying to calculate the mass of the sulfur, okay? So I'm gonna say mass of sulfur. This is the theoretical. It is going to be equal to number of moles multiplied by molar mass. Now, what is number of moles? Number of moles is 0.01. Okay. What is the molar mass? What is molar mass of sulfur? Molar mass of sulfur, it is 32. How much do I get? When I punch that to my calculator, I get something like 0.01 multiplied by 32. I think something like 0.32. Okay. You get something like 0.32 grams. Now you have found the theoretical and the actual you were already given. So the last step will say, okay, therefore the last step, percentage yield, it is you can just write the formula, it's fine, which is the actual divided by theoretical multiply by 100. So let's just substitute and see how much we get. Actual, it is how much? The actual is the one that they got, which is 0.18 grams, divided by theoretical, it is 0.32 grams. Okay, you don't need to substitute SI units. Multiply by 100, how much do we get? How much do we get? 0.18 divided by 0.32, I get something like multiply by 100, 56.25 what percent. Okay, can you see already we already knew the answer. Here they gave us the answer here as 56 point. In a question paper I'll never get this. Okay, I took it from one of the textbooks. Okay, it is called paper 2, terms and definitions, chemistry, free state. Okay, yes. So we just got the same answer as they asked, the 56.25. So yes, this is what we try to understand. Let me try to repeat here. When you want a percentage yield, it is actual yield divided by theoretical yield multiplied by 100. Now the actual yield, it is the one that they get when they do that experiment practically, okay? Then the theoretical, it is the one that you have to calculate when and try to estimate how much you might get, okay? So the first thing that I remember every time in chemistry, I try to find number of moles, okay? I found number of moles of the limiting reagent because it is the one that's gonna become complete again, become that will cause the reaction to stop again. So I know when the reaction stopped, this one is reacted completely and it formed exactly these number of moles of those again. Then now I say, okay, now I found number of moles of hydrochloric acid and I use this formula CV because I had concentration and volume. Again, first thing I did, I did that I converted the volume to decimeter cubed, then found the number of moles of hydrochloric acid and used now what mole ratio between HCl and the sulfur product, which it is what 2 is to 1. Can you see there? Is to 1. Then I use cross multiply, then I get X, which is the same as number of moles of sulfur is 0.01. Then I get the mass using the general equation. Therefore, the mass that I get, it is what the theoretical, it is the one we calculate rona again. Then I come to this formula thereof. Then it is the same as percentage purity. Sorry, percentage purity. It is the mass that is pure will be less than the mass that is impure times 100. Why? Because the pure one, it is the one that they get after filtering. Filtering. Again, this one is the one that we have basically right now. Okay. On this question in percentage purity, they give you the impure they say find the peon. Okay, yes. So thank you very much, folks, for being with me on this question. Please follow me up on the next question, okay, that you're gonna do under the very same topic. Thank you very much, folks. If you see any mistake, please leave it on the comment section. I'll try to address it. Thank you.